Hello viewers and welcome to a new STM32 World tutorial video. In this video we are going to talk about FreeRTOS, a real-time operating system, or so they call it. I'll get back to that. Running on the STM32 MCUs. Let me just show you, it is showing at the moment. I am using my STM32 World, my own development boards, which is a stackable concept. If you look at this, you can see the top board is actually an STM32 F405, and the board immediately below it is a ST-Link flash tool. I should mention that everything in this video, I have created a page on my wiki, the STM32 World Wiki, called the STM32 FreeRTOS, and pretty much everything that I'm going to say today is in this, on this page. So have a look at that if you are impatient. I also would like to mention that I created a project called STM32 World_FreeRTOS in the STM32 Fun repository. I am going to start a new project today, just because I made so much in this project that I forgot and I can't be bothered to fix that. So we're going to create a new project about it. Let's talk briefly about FreeRTOS and my history with FreeRTOS. Some years ago I did some project with ESP32, and ESP32 is a dual core MCU with built-in Wi-Fi and Bluetooth and stuff like that, and it relies heavily on FreeRTOS. In fact, you can't really remove FreeRTOS using the Espressiv's toolchain. It is built on top of FreeRTOS. Everything is built on top of FreeRTOS. And back then I grew to hate this because it slowed down a lot of things, and it was just impossible to get around. So in short, I grew to hate FreeRTOS on the ESP32, and I don't know if I like it better now, but I certainly like the implementation on STM32 a lot better than I like the ESP32. Now, FreeRTOS in itself have a somewhat messy API, and I don't like that very much, but on STM32 there is an abstraction layer pushed in between FreeRTOS and the STM32, and that is called CMSIS. That is actually made by ARM themselves, the people who designed the core in the STM32, and two different versions exist, version 1 and version 2. It's documented here. Now, most of the good documentation that is out there is actually written about V1. But I think V2 changed a lot of things for the better, so I am in fact going to use V2. I also like at this point to point out some of the documentation, in particular two documentation links. I have linked them down here on my page. First of all, this one, which is a presentation, PowerPoint presentation, that goes through everything in FreeRTOS in great detail. It's an excellent source. Unfortunately, it is written for version 1. So I would also like to point out this one, which, here we go. Let's see if that works. My internet has been a bit weird all day. Oh, it actually doesn't work right now. Oh. It's probably my fault. Never mind. But it's a document that describes the differences between version 1 and version 2 and what you need to be aware of. So, without any further ado, let's get started on a project in STM32 CubeIDE. So we select a new STM32 project. As always, I'll go through this. Normally in the last 15 or 20 videos. I haven't done this, mostly because I don't want to repeat myself, but let's do this one from scratch. F45RGT6, that is the CPU we are using, and I will call this STM32 world underscore FreeRTOS 1. Finish. One of the things, while this is loading, it can take a little bit of time the first time. One of the things I should mention, I mentioned I didn't like FreeRTOS on ESP32, and it's because everything is built, all APIs from Espressif on the ESP32 is built on top of FreeRTOS. In STM32 it's the other way around. Nothing changes at the low level or the hell, even the hell interface. Everything is as it is. You just have FreeRTOS running on top of this. So what do we need to get this started? As usual, I go into the system core, I configure the serial wire interface. Let's use serial wire in this case. I also configure the crystal. I go over to clock configuration. I switch to this one. I have a 16 megahertz crystal, not 25, and I want this to run at full speed, 168. Let's see if they can sort that out. It could. So now we have the clock configured and we have the debugging interface configured. The next thing we need to do is to configure our serial port, and I will go down here. I will use asynchronous, and I will blow this up to 2 million bps, which is pretty much the highest I can run stable, but I'll do that. I'll also go over here and I'll configure my LED. So I'll configure this one as a GPIO output. Let's see. We call that LED. And we go into the GPIO here and we default to high, so the LED is off, and we'll make it open drain. All this is pretty much what I have been doing in every single project. Now let's generate this just to verify that that is working. So we basically generate the code, and the first thing I do when we get this code is to change this one to me. There, and I paste a bit of code down here, which basically redirect the serial port. I had that ready. I redirect the serial port to the UART, and let's just verify that that is working by going down here after we initialize and say printf. I like to make a few empty lines. And a new line more. That's basically it. So let's just verify that that is working. Let's see. We have something running already on the CPU, but let's try to build this and just verify. Oh, we need to select the debugger. I'll just, okay. And there we go. So the print works. The printf is redirecting to the serial port, okay, we got a warning here. Let's clear that warning. It basically complains that we didn't include stdio.h. If we build again, just click there. That should be it. So now we have a basic STM32, the basic framework running. So let's enable the FreeRTOS part of this. In the STM32 CubeMX, you go down to middleware and software packs. If you haven't got this already, you might need to go in and select components, and you can see you have it up here. Where is it? Or is it down? FreeRTOS, it's down here, I think. I don't think it needs to be separately installed. I think it is installed by default, but it might. Let's see. But you go down here in the STM32 CubeMX, and you can enable, as mentioned, V1 or V2. We are going to use V2. So I select V2 here, and then we'll see we have quite a lot of configuration possibilities down here. Let me briefly explain the concept of FreeRTOS, and I'll go back into my article here. The basic concepts in FreeRTOS is you have an concept of a task. Now, I don't really understand why it is called a real-time operating system. It's just one of those terms that everybody is using. But in reality, what it is it's a task switcher. We only have, or task manager, we only have one core in the STM32. So in order to execute two different tasks, it will have to run one task and then switch over to the other one, and then switch back and forth between these. And that is essentially what FreeRTOS is doing. Everything evolves around a task, and a task, as you can see down here, a task is always an endless loop, exactly like our main loop in any application that never exit and keep running. And task can operate in one of four different states. It can either be running, or it can be blocked. Blocked basically means that it is waiting for some kind of event. I'll get back to that. Or it can be suspended, meaning it's no longer running, or it can be ready to do something. If we look at the actual, I'll get back to that. The next part of these concepts is something called semaphore. A semaphore flag is a flag, and it is basically used to synchronize two different tasks. So if you have one task, it can be waiting for a semaphore, and the other task will then release or set that semaphore, and that will trigger the first task to continuous execution. So it basically makes it synchronized between tasks. Mutexes is used to get exclusive access to something. It doesn't matter what it is, but some kind of resource that can only be handled by one task at the time. You will use a mutex, and the task will need to get exclusive access. That means acquire a mutex, and then when it's done doing whatever it's doing, it will release that mutex. If another task tries to get access at the same time, it will try to acquire the mutex, and it will wait until that mutex is available. That means it's released by the first task. The last concept that we are going to go through today is the concept of queues. Queues are used to send messages between tasks. So you can basically have one task sending a message to another task, and the other task can wait for those messages or check periodically whether there are messages available in the queue, and then respond appropriately to those messages. So let's go over here and see in the user interface. You can see up here we have a tab for mutexes, we have a task for tasks and queues, and we have timers and semaphores, and we have this tab, which basically sets all the configuration parameters. For now, we are probably going to have to change some of them, but let's leave them empty for now, and let's create a few new tasks. So you'll see we initially have one task, which is called the default task. It's running at normal priority. We can set that to low or high. There are a lot of different priorities. You see there's a stack size defined here. Each task in FreeRTOS has its own memory. that is allocated by FreeRTOS on the heap of the STM, but it's sort of a secondary heap. It's managed by FreeRTOS and the task. You can see we have an entry function and well, a few other options here. Let's create a new task, and let's create, I mean, what I'm going to do in this video is not going to make sense. It's just I'm just trying to demonstrate as many of the features as possible in the shortest amount of time. But let's do let task. That task will just flash the LED. It was running a low, and we'll have a function we call start LED task. Let's also create a task to print out our usual tick messages rather than so we could call that tick task, and we say start tick task. So now we have a couple of tasks. Let's start by looking at the code, what it actually generates for that. We need a little bit more in here, but let's try to generate the code and see what actually happens. Okay, we get a warning here that RTOS is strongly recommended to use a hell time-based source other than the sys tag. No, I don't want to. I want to fix that. So basically what they're saying is that they prefer to have FreeRTOS using the sys. If we go in here, wait, here, you can see that time-based source is sys, but FreeRTOS would like to use that one on its own. So what we can do here is we can actually say another timer, and let's select timer 14. So if we set timer 14 to run the normal STM32 stuff, and then we use the sys to run the STM32. So let's try to generate the code. Is another warning? No, and that one is actually down under the it's a little bit irritating. Down under FreeRTOS, we need to go under advanced settings, and we need to enable this feature. I didn't really read the error message, but let's just say, let's trust them for now, and let's try to generate the code. There you go. So let's look at what code it generated. First of all, it includes the CMSIS RTOS. And then we define some variables here, which is basically a couple of variables, some thread attributes and a thread ID variable. And these variables get set here. It is notice that the stack size is actually set for each. If we go back over here, you can see up here, we can see the stack usage. There. So we have used 1,896 bytes out of, I don't know how much it actually allocates. I think that is set down in config parameters. Where is it? Minimal, no, here. So 15,360 bytes, it's a total heap size, and we have used 1,800. That is all configured in here in the task attributes, but these task attributes is set by the UI. Then we go down in our main loop. After we initialized everything, we see first we initialize the kernel of FreeRTOS, and then we define these task handles. So we basically fire up the task, and then we start the kernel. And we should notice that it never gets down here. If we go in here and say, okay, we'll print out something weird happened, you'll see we have our print up here, and then we get down to that. If we try to execute this, it will be starting. It just did, but it never gets to this point. So it basically stops at that point. Now, if we look at the task, they are defined here. So we have start default task. That is our default task that just loops around, and you can see the loop is an endless loop like our regular while loop. If we use that anymore, we don't. It never reaches that, but it will have a loop here, and all this loop is doing, it's waiting for 1 millisecond, and then it will reloop. You'll see our let task is exactly the same, and our tick task is exactly the same. So we now have 3 tasks that are looping around, waiting for something to happen. Right? Now, we could, for example, it would be the most obvious, we could expand our let task here, and let's try that. Let's say, okay, rather than wait, we can just wait for 500 milliseconds, and then we can do a hell GPIO toggle pin, and we have our let port and let pin. Let's try to fire that up, and let's see on the device what happens. There you go. It is blinking every 500 milliseconds. So essentially this task, but notice that the other tasks are still executed, while this one is doing OS delay. All the other tasks can execute. So we could start doing every single task. So let's try to make these different tasks work together in a different manner, just to illustrate that. And first of all, let's create a semaphore. So we do a binary semaphore, which we call let semaphore. That's it. So now, if we want to synchronize 2 tasks, we can actually signal from our main task that we want to blink the LED, and then we have another LED, another task actually doing the blink. Let's generate the code for that. And we go back to main. Now I am going to take a little shortcut here and not reinvent the wheel, because I already went through this. So let's do our own other main here. And let's grab our, where is it? Where's in let task here? Let's grab this let task completely. Go back here. Where is our let task? So rather than doing this in the let task, there. So we have now changed this let task. So rather than having the delay, we are trying to acquire this let semaphore, and we'll wait forever for that. And if we get it, we need exclusive access to handle the pin. So we actually need to create a mutex, and we call that let mutex. So let's go in here and create a mutex as well, and we call that let mutex. I could spell there. Generate the code. There you go. So now the let task is actually not doing anything except toggling that let pin if it get a semaphore from another task. And let's look at how we actually did that in our loop town. Wait, put semaphore release. So what I'm doing is we go in here. Up in our default task, rather than having a OS delay of 1, we do an OS delay, so 100 milliseconds between each of these. Then we will increase a counter. So let's do a loop counter. it will be up here. We do a loop counter, and we need to increase that loop counter. So we do that down here, and then we can respond if we can count up. We have that there. So basically add one to the loop counter every 100 milliseconds, and if that is divisible by 5, which it will be every 500 milliseconds, then we release that semaphore LED, which will then trigger our other task over here to flash the LED. Let's see if that works. It started, and let's look at the device there, and you see it still flashes the LED every 500 milliseconds, but in a slightly more complicated manner this time, as it gets a signal from the default loop will send a semaphore, release a semaphore, which the LED task will then grab on. It will acquire a mutual access to the LED GPIO pin. It will toggle the pin. It will release the mutex. We could have multiple tasks actually handling this in the same manner. They would never do it at the same time, but they would. So next step, let's try to make a print something, the tick. In order to do that, I want to add one more mutex. Let's call that a print mutex. It is pretty obvious that every time we print something out, we end with a new line, and we don't want two tasks to print half and then a new line. It will mess up the print output. I don't think anything bad would happen, but it would mess up the printing. So let's do a print mutex, and this time let's actually use a queue. So we go in here and we add a queue, and we could call that tick queue. Tick queue. We mix, and we item size. We can use UNT32 T to so 32 will simply send the counter from a default task over to our tick, and tick will print it out. So let's try to. So now we have a tick queue, we have a tick task, and we have a print mutex. Let's again generate the code. There, and then we go into, you see what I'm doing here, every 10, so 10 times I can grab that and copy it into our default task up here. So every 10 times we will get the tick from the OS kernel get tick count, and we'll put that on the message queue. Let's see if it builds. It did. So now we can look at how I implemented the tick task. For now, let me just copy it and find our tick task down here. Paste that in. So you can see again we have a forever loop running here. We have a tick variable in here, a local variable. We wait for a queue message. In the tick queue, we get the value put in there, and we wait forever for a message. If this one returns OK, then we acquire the mutex on the print, and we print out this, which is stupid. Hang on, we don't need all that right now, so let's remove that part, and we only print the tick. So there we go. Let's try to build this, and it builds. Let's try to run it and look at the output here. There we see we got a print. So we now have that running, and let's look at the device there. it blinks. So we now have 3 tasks running, and these tasks communicate. Our default task will send a message every second to our tick queue, which will be picked up by the tick task, and it will release a semaphore every 500 milliseconds, which will be picked up by our LED task. So 3 tasks that interact with each other in different ways. Now, I actually had some more plans with this video, but I think it is long enough now, so I will get to that in the next video probably. So whatever we have in this video will be in FreeRTOS 1 project, which will be committed to our repository. Next time we'll do a FreeRTOS 2 for the second video in this series, and so on and so forth. I really don't know how long we are going to get with this, but I have a few ideas. You can already see that if you go into the FreeRTOS project, where I'm doing some interesting stuff. But let's leave it at that. As usual, if you feel that this video was worth anything, please do like and subscribe below. It really helps a lot with the YouTube algorithm. And as usual, I love the comments and I love to respond to them. So if you have any questions, comments, anything, please add them below. Have a wonderful rest of the day.